business on that. All right, so re-expression. Is the process of applying a function to the data in order to make a scatter plot straighter, and then to apply a regression model, or to make a distribution more symmetrical. So we know that if the scatter plot's not straight, then applying a linear model to it doesn't make any sense. You may have noticed on either of the calculators that you're using that they ask you, do you want to do a linear? And then they have all these other ones as well, right? So what they're doing when they're doing a quadratic is they're actually taking the data, taking the square root of it, or taking some sort of square root of it, and then applying all the rules for the linear model. They just don't tell you that that's what they're doing, but that's kind of, and that's an oversimplification, but that's kind of what they're doing. So the two goals of re-expression, one of them is if you have a histogram that looks like this, could we apply a normal model to this? No, there are outliers aplenty, right? So you're like, okay, I don't know anything about this then if I can't apply a normal model to it. So one of the goals is to make the distribution of data more symmetric. So this is hugely right skewed with outliers. However, if instead of doing the compensation, this is one where you look at how much do CEOs make. And I don't remember what the SM stands for. Oh, it's a dollar sign?
Yeah.
So it's in millions of dollars, right? So you have a lot of CEOs that are down in this range, but you've got some that are making some serious coin, right? If though we take the log of the compensation and then redo it, we get something that's way more normal-ish, right? And so we can apply some ideas to that we know from a normal model. So we're trying to make it fit one of our models. And basically the two models that we use normal model, and that gets used a ton, and we use for scatter plots, we use a linear model, and that's pretty much it. Those are the two models that we use. So what's going to happen as we get further on is a lot of times we're going to have to look at, can we apply a normal model to this? Some of those first things you have to look at is, does our model fit this or not? So that's one thing that you may have to do. Oh, and I didn't even notice this the first time I did this. Down here, this is the box plot with all the bazillion outliers marked.
What a plot.
Pardon?
I said, what a plot.
Yeah.
It's a great plot.
There's almost more outliers than there is anything else. At least it feels that way. All right. So the other goal is if you have multiple groups, you can't really compare these very well the way they are right now, right? Because this is so compact here, and this is spread out like this. So one of the other goals would be to make the spread of multiple groups more like. So this is smoke exposure. And I'm trying to remember what ETS stood for. It's basically secondhand smoke, I think is what that was. So none, some, ETS, and actually someone who smokes. And this is the Cont 9 levels in their body. I don't know what that is. Biology is one of those things that's primarily a mystery to me. Does anyone know what it is? I think it's bad.
Yeah, I would agree.
Other than that, I don't know. But here, if we take the log of this output, now we get something where we can actually look at these box plots and we can make some comparisons.
So why would you do the log to like the the y-axis and not the x-axis?
Because the x-axis is not quantitative.
Oh, you're right, I see it.
Yeah, and when you go back to like one like this, it's like, okay, this is a count, so it doesn't make sense to take the log of a count, but it does make sense to take the log of this.
Yeah.
Logarithms is one of the ones that gets used more than anything else. Logs and square roots. Speaking of which, or squaring. So the third thing that we want to do is to make the form of a scatter plot more nearly linear.
Physics.
What now?
I think we've done this in physics, the squaring part. Except we use that at Logger Pro.
Oh, okay.
We'd use data and we'd square it to make it straight.
Gotcha. So to make the form of a scatter plot more nearly linear. Because then we can talk about things like the correlation. We can talk about, what percentage of the variation in one variable is accounted for by the variation of the other one. When it's not linear, we can't do any of those things. So notice here what they did is they squared the output. Because this looks kind of like a square root graph, right? So by squaring the output, well, it'll kind of straighten that out. And also sometimes to make the scatter and a scatter plot spread out more evenly rather than thickening at one end, where you have, maybe you have small residuals and then it kind of, the residuals spread out. You get bigger and bigger residuals. All right, so this table down here is called the ladder of powers. And as I said earlier, for doing homework and stuff, this may be really important to you. Memorizing this for my test or for the AP exam, probably not. Okay? So, if it appears that your data may be helped by re-expression, try one. And literally, try one. I usually start with square root or square or log. Those are kind of my go-tos. And if it helps, but not enough, then move the next level down. So 1 is the raw data. So if you take the square root and you're like, oh, that's better. Well, but it's not better enough, then try doing a logarithm instead. After that, it starts to get a little nutty. You can take the negative reciprocal square root.
So you do this on top of the one before it, or do you take the original?
You go back to the original. You're always going back to the original data.
I was wondering the same thing.
Or just take the opposite reciprocal. Now, there are some comments on why you might want to do this. So for example, squaring, if you have something that's skewed left, which doesn't happen all that often, or scatter plots that look like the square root graph, like this one did, then you can square the data. Okay? Counts often benefit from the square root reexpression. So you actually can take the square root of counts, although that seems kind of counterintuitive. You can do that. Sometimes it's helpful
Wait,
because the count is a numeric value.
is that like the frequencies?
Mm-hmm.
Oh, okay.
Counts, frequencies, same thing. Now, when you're applying logarithms, you got to be careful. Data can't be negative because you can't take the logarithm of a negative value. What can happen if the data includes any zeros? Sometimes they'll just add a little constant to it to make it so where they're not, which feels like cheating. This negative reciprocal square root doesn't get used very often. The reason you want to change the sign is it preserves the direction of the relationships. So your correlation direction will be the same as it was before.
All
To re-express data,
to make it more.
to make it more linear, to make it more normal,
Okay.
So we can read it better.
so that you can use something that we already know to be able to analyze, make predictions, all that kind of stuff. Sometimes you have to fall back on plan B. When none of those straighten things out enough. And you can see where I'm talking about, you kind of guess, and then it can be a really long process if you guess wrong the first time. You're like, okay, I'm 4 into this now, and it still isn't particularly straight.
Yeah, at that point, might make us move on.
Yeah, and this is why they don't ask it on the AP exam, honestly. So you can take the log of y, you can take the log of x, you can take the log of both of them. And typically we just use we use the log base 10, right? The common log. I do like their comment. I copied this from the book. This is called the Goldilocks model. When one of the ladder's powers is too big and the next is too small, this one may be just right. Cracks me up. I'm like, okay. All right. Notice this one, when you have a wide range of x values or a scatter plot descending rapidly at the left, but leveling off towards the right, that may be helpful. That's the one we did with the CEOs. We took the log of the input values. All right, and again, just to say this another time, figuring out the best re-expression can be a time-consuming task. So on your homework, if you're asked to guess one, right, and it doesn't work, try another, but after that go, yeah, I'm done. Okay? Don't spend forever trying to get the perfect re-expression. So here's what the College Board says you need to know. So it says calculate a predicted response using a least squared regression line for a transformed data set. So the transformed, that's the re-expressed. So they could give you a data set and they could say apply a log to this. So what are you supposed to know? Transformations of variables, such as evaluating the natural logarithm of each, and they use natural log here. Your book tends to use log base 10. It really doesn't matter. Of each value of the response value, or squaring each value of the explanatory variable can be used to create transformed data sets which may be more linear in form than the untransformed data. Now, how is it that you're going to know that your new one is better? I think this is kind of the more likely question. Increased randomness in residual plots, right? You don't want residual plots to have any kind of a pattern. So if after they've re-expressed it, the residual plot is more random, that means that the new one is better than the old one. It doesn't mean the new one's perfect. It just means it's better than the old one. Or if you get an R squared value closer to 1 or to -1, that offers evidence that a least squared regression line for the transformed data is a more appropriate, not perfectly appropriate, but more appropriate model to use to predict responses to the explanatory variable than the regression line for the untransformed data. Okay, I think that's the kind of question you're more likely to get on an AP exam, where they give you a scenario, give you all this information about it, and they're like, is this really better or not?
And just look at the residual plots.
You can look at the residual plot, or if it's they've done a least squared regression for it, then you can look at, is the R squared value closer to 1?
Oh.
Or is the R value closer to +1 or -1?
So it's really, that part is pretty easy. It's just understanding like the stuff behind that. It's kind of the more complex parts.
Yeah. So like I said, you're going to be taking some shots in the dark on some of these.
Sorry.